Okay, hello everyone. I'm Yeonhong Park from Seoul National University. Today I'm going to present my paper titled DecDEC. This work was conducted in collaboration with my colleagues at SNU, including Jake, the co-first author, Hojoon, and Professor Jay Lee. Running LLMs on personal devices such as desktops or laptops offers several advantages. It ensures privacy, it does not need for an internet connection, and provides low latency. One important characteristic of on-device LLM inference is that it is typically single-query processing. In most on-device scenarios, the system handles only one queries from one user at a time. This is fundamentally different from data center setting, where multiple queries from many users are processed together in batches. Because of this characteristic, on-device LLM inference is highly memory-bound. This is because every linear layer in the model is reduced to metric spectral multiplication, or GenV. For this reason, for on-device LLM inference, quantization needs to be done differently. Different from traditional practice where both weights and activations are quantized to leverage low precision compute, on-device LLMs often use weight-only quantization. Here, only the weights are quantized and dequantized on the fly for the computation. And this approach focuses only on memory bandwidth reduction because there is no need to save computation. By doing so, this approach minimizes accuracy loss due to activation quantization. The key benefits of quantization are reduced GPU memory consumption and lower latency. However, at the same time, it inevitably leads to some loss in accuracy. And our goal is like this. We want to recover accuracy loss from quantization. And we wanted to achieve this without sacrificing the two key benefits of quantization, which are reduced GPU memory consumption and lower latency. This might sound too good to be true. As you know, in engineering, there's no free lunch. To gain something, we have to pay something. And in fact, we do pay a price. We trade off a resource that we believe to be less critical in the context of LLM inference. And that is CPU memory. In other words, we use a little bit more CPU memory to improve accuracy of quantized LLMs without introducing any GPU memory or latency overhead. Our approach targets specific platforms. We assume a typical desktop or laptop where CPU and GPU have their own memory connected via PCIe. And the baseline system looks like this. First, the quantized weights, what we denote as W hat, are stored in GPU memory. And meanwhile, the CPU stores are the residual matrix. The residual matrix is the difference between the full precision weights and the quantized weights. In this setup, we bring the corresponding residual matrix from the CPU to the GPU for every GenV operation. In this way, we can achieve the exact same result as running inference with full precision weights, and this is a very simple idea. But of course, this idea doesn't really make sense in practice. The residual matrix is just as large as the original weight matrix, so sending it over the slow PCI link for every GenV operation is not feasible. It will be really slow. So we changed the design. We bring only a selected subset, not the entire residual. Here, M is a binary mask that selects which subset of the residual to bring over. And this leads us to the key question. How should we select this subset? In other words, how should we construct a binary mask M? To maximize the effect, a good mask needs to select only the most important portions of the residual. The time margin we have to work with is actually very limited. On typical consumer-grade GPUs, the PCI bandwidth is 20 or 30 times smaller than the GPU memory bandwidth. Second, the selection needs to have some structure. If not, it may be extremely difficult to implement it efficiently. To tackle this problem, we focused on one key observation. Not all channels in the weights are equally important. From now on, I'll be using the term channel, and you can just simply think of channels as the rows of the weight matrix. Let's consider a simple example where a 4-element vector is multiplied by a quantized 4x4 weight matrix. In this case, the first element of the vector is multiplied with the first channel of the weight matrix. And the second element is multiplied with the second channel. The same goes for the third and first element. When you look at the activation vector, we often find some elements that are much larger than others. These are commonly called activation outliers. In the context of quantization, the channels that are multiplied by these activation outliers become more important than the other channels. This is because when weights are multiplied by a large activation value, the quantization errors in these weights are amplified accordingly. We call these channels as Salient channels. In this example, if we were to add the residual to just one channel, it would naturally make sense to choose the Salient channel, which is the solved one. But there is one problem. The position of the activation outlier keeps changing. This is the input. Sometimes it's the third element, sometimes it's the first element, and it can also be the first element. In fact, what you see here is the distribution of activation outliers at each decoding step. While there are some weak patterns, in general, the positions are highly random. To address this issue, we propose DecDEC. First, let me explain how it works. A transformer model typically consists of blocks that repeatedly apply 4 types of linear layers. We extend each of these linear layers as shown in this diagram. The base GenV is simply the original GenV operation, which multiplies the quantized weight with the input. What we add on top of this is a new component called dynamic error compensation, or DEC for short. This involves multiplying a subset of the residual fetched from the CPU with the input. These two operations are executed in parallel on the GPU by leveraging its stream feature. Inside the DEC, the following 4 operations are performed. First, we apply a top K operation to the input activation vector to identify the indices of the Salient channels. Next, we fetch the residuals corresponding to these identified Salient channels from the CPU. Using this, we perform the residual GenV. And finally, we combine the result with the base GenV output. The mechanism itself is not that complicated, but implementing it efficiently turned out to be extremely challenging. So next, I would like to share some key points regarding our implementation and optimization. First, one of the key issues was deciding how to bring the residuals from the CPU to the GPU. There are 2 main approaches for transferring data from the CPU to the GPU. The first approach is block transfer, which is to utilize widely used APIs like CUDA and copy. This is good for sending a large chunk of data, but it can be inefficient when sending multiple small pieces of data. You first need to gather the data into a contiguous buffer before sending it to GPU. The second approach is a zero-copy-based method. In this case, the GPU cores directly issue memory requests to the CPU memory. This allows for lower latency and enables cache line size data transfer. The main drawback of this approach is that it consumes GPU cores. In our system, zero copy is the answer. First of all, latency is extremely important for us, and the access granularity is relatively small. We access the residual metrics at the channel levels, which typically amounts to just a few kilobytes. And in our setting, consuming more GPU cores is not a problem at all. The base GenV kernels, which runs in parallel with residual fetching, is extremely memory bound, and it means that the GPU cores are highly underutilized. Moreover, by using zero copy, we completely bypass GPU memory. It eliminates any risk of memory bandwidth contention. In a way, this is almost a perfect use case for zero copy feature. Making effective use of the zero copy was the most important point, but it also applied several other optimization. First, we quantized the residuals themselves. Of course, this quantization introduces some approximation error, but we believe that being able to bring in more channels would ultimately outweigh the cost of that error. We also put a lot of effort in optimizing the GPU kernels. DEC requires a top K operation, but top K is not very GPU friendly. So we implemented an approximate version of top K that is more suitable for GPUs. In addition, we fused all 4 operations of DEC into single kernels to minimize latency. Finally, let me talk about the configuration, specifically how to set the system parameters of DecDEC. There are 2 main system parameters in DecDEC. The first one is called NTB. As you know, in DecDEC, the base GenV and DEC kernels run simultaneously. So we need to allocate resources. Specifically, we need to allocate GPU cores between these 2 operations. And NTB controls how many cores are assigned to DEC. If NTB is too small, that is, if too few cores are allocated to DEC, we won't be able to fully utilize the PCI bandwidth. As I mentioned earlier, we use zero copy. So the memory requests come directly from GPU cores. So having too few cores limits data transfer throughput. And on the other hand, if NTB is too large, the base GenV may slow down. Taking some cores from base GenV is okay, but if we take too many, the base GenV would get slower. The second parameter we need to set is K. This is the number of channels fetched from the CPU. If K is too small, we can't fully utilize the available time slack. If it's too large, DEC itself becomes the bottleneck. Ideally, we want to find the K value where the latency of base GenV and DEC are perfectly balanced. These 2 parameters are interdependent, and both of these parameters can be set differently for each layer. As a result, the design space becomes very large and complex, so we need an auto tuner that can automatically find the right parameter settings. The tuner takes 3 inputs: the model architecture, GPU device, and the latency budget. The latency budget specifies how much slower the latency can be compared to the vanilla quantized LLM without DecDEC. Based on these inputs, the tuner outputs the probability and K values for each layer. The tuner basically adopts a greedy search strategy with several heuristics to reduce the search space. For details, please refer to the paper. Now let's move on to the result. There are 2 key results. First, I will show how well the kernel is implemented. As long as NTB and K are properly set, DEC overlaps perfectly with the base GenV. We ran experiments on 3 different consumer-grade GPUs. What we measured is how much slower the kernel becomes when adding DEC on top of the base GenV. The red-marked graphs represent cases where NTB is properly set for each GPU. As you can see, for these cases, there is no latency increase at all until the K value grows beyond a certain point. The results stay flat right around 1.0. This means that DEC is successfully overlapped and fully hidden. And this is exactly the behavior we expected, and it confirms that our kernel is well implemented. Second, I will show that when we run the end-to-end system built on top of this kernel using the parameters selected by our tuner, we can significantly improve accuracy, minimizing any increase in latency. This is the result. I guess this is the type of graph that you have never seen. So to simplify, let me zoom in. There are 3 lines here, each representing results from a different GPU platforms. The vertical axis shows perplexity, so the lower the better. The horizontal axis represents latency. The X marks represent the result of the vanilla quantized LLMs without DecDEC. Below them, you can see 4 circles. This corresponds to cases where we set the target latency overheads to 2.5%, 5%, 10%, and 20% respectively. As you can see, even with just a 2.5% target, perplexity drops significantly. Take a look at the area highlighted in red. When we apply DecDEC to the 3-beam model with the 2.5% latency target, the perplexity actually becomes better than the 3.5-beam model. Memory usage remains the same as the 3-beam models, and the latency is also practically at the 3-bit level. In other words, This result showed that our initial goal, which is to boost accuracy without increasing GPU memory usage or latency, has been successfully achieved. Of course, as you can see, increasing the latency budget doesn't lead to proportional perplexity improvement. Beyond a certain point, the gains become very marginal. So in conclusion, the setting we recommend is the 2.5% target. Now let's zoom back out and take another look at the full graph. As you can see, the same trend is observed across different models, different quantization methods, and also different GPU platforms. Now it's time to wrap up. DecDEC is open source, so please check out the QR code if you're interested in. And thank you for listening. And I'm happy to answer any question.